In 1846, a mathematician calculated exactly where an unseen planet had to be before any telescope confirmed it. He was right. 6 frozen worlds at the edge of the solar system are now behaving the exact same way, pulled by something nobody has ever seen. The math says it's there. The sky hasn't shown it yet. But if the pattern from 1846 is repeating, why hasn't anyone actually seen it yet? We trace the century-old hunting method that once worked perfectly, meet the observatory built to try it again, and look at the discovery that's starting to complicate the story. One thing before we start: if cosmic mysteries like this are exactly what keeps you coming back, subscribe. It helps us reach more people who think the way you do. We're genuinely glad you're here. Now, let's begin. Start with the sun. If you shrank it down to the size of a basketball, Earth would be a grain of sand orbiting about 26 meters away. Neptune, the last confirmed planet, would be a pea, drifting nearly a kilometer out. That's already an enormous gap. But Neptune isn't where the solar system ends. It's closer to where the quiet part begins. Beyond Neptune's orbit lies the Kuiper Belt, a disk of icy debris. Pluto is the most famous resident, stretching out to roughly 50 times the distance between Earth and the Sun. Past that, the population thins out further into what astronomers call the scattered disk. And beyond that, a handful of objects exist on orbits so wide, so slow, and so faint that each one takes thousands of years to complete a single loop around the Sun. At that distance, sunlight itself takes days to arrive. A world sitting out there wouldn't glint or streak across the sky. It would sit still, for years at a time, buried in a field of a billion other faint points of light. This is the part of the solar system where a large object could hide in plain sight, not because it's actively concealed, but because there is simply too much dark, too much distance, and too little light to search it all at once. Here's why that's not an exaggeration. Anything we see in the outer solar system, we see by reflected sunlight. There's no other light source out there. Light has to travel out to the object, bounce off it, and travel all the way back before a telescope ever registers it. That round trip weakens the signal twice over, and the weakening gets dramatically worse with distance. Push an object 4 times farther away, and it doesn't look 4 times fainter. It looks roughly 250 times fainter. Push it to the distances we're talking about here, hundreds of times farther from the Sun than Earth is, and even a world several times the size of Earth would appear as little more than a dim smudge, one among billions of similarly dim smudges, background stars. Distant galaxies, faint asteroids, all crowded into the same images. Add to that the sheer size of the search area. A survey doesn't just need to look in the right direction. It needs to look at the same patch of sky more than once, days or weeks apart, and notice that one single point of light has shifted while everything else stayed put. Do that patch by patch across the entire sky, and you start to understand why searches like this have historically taken years, not evenings. It isn't that nobody has looked. It's that the sky is an almost incomprehensibly large place to search thoroughly, one telescope and one patch at a time. Go back to that basketball-sized sun for a moment. Neptune's pea sat roughly a kilometer away. A world at the distances this video is actually concerned with, several hundred times farther from the Sun than Earth would be sitting 10, 15, sometimes 20 kilometers out from that same basketball, not simply farther than Neptune. Farther than Neptune by the same kind of margin that separates a walk down the block from a trip clear across a city, and dimmer at every one of those extra kilometers, not dramatically less so. That's the setting for the question this video is built around. Is there a planet out there we haven't found yet? Not a rumor, not a conspiracy. A real, still open scientific question. argued over in peer-reviewed journals by people with telescope time and reputations on the line. To understand why serious scientists take that question seriously, you have to go back to the last time this exact situation played out twice. Once, the math was right and it found a real planet. The other time, the math seemed just as convincing and it found nothing at all. Both stories start the same way. They end very differently. That difference is the whole reason this hunt is being taken seriously today. By the early 1800s, Uranus was a problem. It had been discovered in 1781 by William Herschel using a homemade telescope in his garden in Bath, England. Herschel wasn't even looking for a planet. He was systematically cataloging faint stars when he noticed one that looked slightly different, slightly too large, and that moved against the background over successive nights. Every planet known before that point, Mercury, Venus, Mars, Jupiter, Saturn, had been visible to the naked eye since antiquity, tracked by every civilization that ever looked up. Uranus was different. It was the first planet ever found rather than simply always known, and it doubled the known size of the solar system overnight. For decades afterward, astronomers tracked Uranus's position carefully, plotting where Newtonian gravity said it should be at any given moment. And for decades, Uranus refused to cooperate. It kept showing up slightly ahead of its predicted position, then slightly behind it, in a pattern that no adjustment to the calculations could fully smooth out. There were three possible explanations. Newton's law of gravity was wrong. The observations were flawed. Or something massive, sitting even farther out, was tugging on Uranus in a way nobody had accounted for. Nobody seriously entertained the first option. Newtonian gravity had already explained too much, too precisely, for too long. So in the 1840s, two mathematicians, Urbain Le Verrier in Paris, and independently, John Couch Adams in Cambridge, sat down with Uranus's observed positions and reverse-engineered the problem. If an unseen planet were pulling on Uranus, its mass and orbit would have to fall within a very narrow range to produce exactly the wobble being observed. Work backward from the wobble, and you could, in theory, calculate where to point a telescope. This is the part worth sitting with for a second, because it's easy to let it pass as a historical footnote. Nobody had seen this planet. Nobody had a hint of light reflecting off it. The entire argument for its existence was a stack of arithmetic, built on the assumption that gravity behaves the same way at the edge of the solar system as it does here. Le Verrier finished his calculations first and made them public, presenting his predicted position to the French Academy of Sciences at the end of August 1846. Adams had arrived at strikingly similar numbers, working independently, and for a while, in complete ignorance of Le Verrier's parallel effort. But Adams struggled to get British observatories to take the search seriously. His results sat for months with the Astronomer Royal, George Airy, who was slow to act on them. James Chally at Cambridge Observatory eventually did begin a search based on Adams's numbers, and, in a detail that still makes historians wince, actually recorded the planet in his observations on two separate nights before Le Verrier's letter ever reached Berlin. He simply didn't recognize what he'd seen in time. Cross-referencing his own notes came later, once someone else had already found it. That someone else was working faster. Le Verrier, frustrated by the French observatory's lack of urgency, wrote to a German astronomer named Johann Galle at the Berlin Observatory, describing exactly where to look. Galle received the letter on the 23rd of September, 1846. That same night, using a 9-inch telescope, he pointed it at the patch of sky Le Verrier had specified. Within about an hour, he found a faint, star-like object that didn't match the star charts. The next night, it had moved. It was a planet later named Neptune, sitting within 1 degree of where Leverrier's pen had placed it. 1 degree at that distance is a needle landing almost exactly where a blind throw predicted it would. Adams's independent calculation had been off by 12 degrees, still remarkably close, for a calculation with no telescope involved, but nowhere near as precise as Leverrier's. It is difficult to overstate how strange this moment felt to the scientists living through it. A planet, an entire world, large enough to be the third biggest in the solar system, had been discovered not by looking, but by doing math and trusting the answer. The French astronomer François Arago put it more elegantly. Leverrier, he said, had discovered a planet with the point of his pen. Neptune's discovery became the gold standard for what a mathematical planet hunt could achieve. It proved that gravity's fingerprints, left on the orbit of something you can see, could reliably point to something you can't, and it planted an idea that would outlive everyone involved. If Uranus's orbit hid one unseen planet, what if it, or Neptune's, hid another? That question didn't go away. It just moved to Arizona and waited 60 more years for someone to take it seriously enough to build an observatory around it. Percival Lowell was rich, self-taught in astronomy, and utterly convinced that a ninth planet was waiting to be found beyond Neptune. He'd already spent years and a fair portion of his personal fortune chasing another idea that hadn't panned out, a network of canals on Mars that turned out to be an illusion of low-resolution optics and an overactive imagination. The hunt for a trans-Neptunian planet became his next obsession, and unlike the canals, this one had real orbital mechanics behind it. Starting in 1905, he poured his own money and the resources of the observatory he'd built in Flagstaff, Arizona, into a systematic hunt for what he called Planet X, a hypothetical world he believed was responsible for lingering irregularities in the orbits of Uranus and Neptune, irregularities that Neptune's discovery hadn't fully cleaned up. Lowell never found it. He died in 1916, the search unfinished, and a bitter legal dispute over his estate shut the project down for years afterward. In 1929, once the observatory was finally free to resume the hunt, it hired a 22-year-old amateur astronomer named Clyde Tombaugh, whose only real qualification was a homemade telescope and a set of hand-drawn sketches of Mars and Jupiter good enough to impress the observatory's director. Tombaugh's job was tedious almost beyond description. Use a new 13-inch telescope to photograph the same patch of night sky several nights apart, then compare the two images side by side using a machine called a blink comparator. The device mounted both photographic plates and flicked rapidly back and forth between them, several times a second. Fixed stars, appearing in the same place on both plates, seemed to sit perfectly still under the flicker. Anything that had moved between exposures, a planet, an asteroid, a smudge of dust on the glass, appeared to jump. Tombaugh worked the comparator for hours a day, month after month, examining by his own later estimate somewhere north of 1 million individual points of light, ruling out one false candidate after another. Most turned out to be asteroids, moving too quickly to be anything as distant as Lowell's hypothesized planet. On the 18th of February, 1930, comparing plates taken 3 weeks earlier, he found one that moved at exactly the right, painfully slow rate. A faint object sitting in almost exactly the region of sky Lowell's calculations had pointed to. The discovery was announced on the 13th of March, Lowell's birthday, had he lived to see it. The new world was named Pluto a few weeks later, its first 2 letters a quiet nod to Percival Lowell's initials. For a moment, it looked like the Neptune story all over again. Math predicts, telescope confirms, case closed. It wasn't. Pluto turned out to be tiny. Genuinely, almost embarrassingly tiny, nowhere near massive enough to produce the gravitational tug Lowell's calculations had called for. It took decades to nail this down precisely, because Pluto is so distant and so faint that measuring its mass directly was nearly impossible without something to measure it against. Early estimates made in the 1930s guessed Pluto might be roughly as massive as Earth, which would have made Lowell's story hold together perfectly. By 1948, refined estimates had shrunk that figure down to something closer to the mass of Mars. Each revision chipped away a little more of Lowell's original justification, but the number kept sliding, and nobody had a way to pin it down for certain. The breakthrough came in 1978, when astronomer James Christie noticed a strange, repeating bulge on long-exposure photographs of Pluto, a moon orbiting so close and so faint it had gone unnoticed for nearly 50 years. He named it Charon. Once astronomers could track Charon's orbit around Pluto, basic physics did the rest, the same math that lets you weigh a planet by watching how fast something orbits it. The result was startling. Pluto's real mass was roughly 1/5 of 1% of Earth's, a small fraction even of the already shrinking earlier estimates. A world that light could no more perturb Uranus and Neptune than a pebble could rock a passing ship. That should have ended the story. Instead, it restarted it. If Pluto wasn't massive enough to be Lowell's Planet X, then logically, Planet X had to still be out there, undiscovered, hiding somewhere near where Pluto happened to be. Astronomer Robert Harrington took up the search in earnest through the 1980s, running new orbital models to narrow down where a real trans-Plutonian planet would need to sit to still produce Uranus's irregularities. He never found it. He died in 1993, the search unresolved for a second time. Here's the part of the story that rarely makes it into the popular version. While Harrington was still searching, the ground underneath his entire premise quietly gave way. In 1989, the Voyager 2 spacecraft flew past Neptune and measured its mass directly, for the first time, with real precision. The new figure was about 0.5% lower than the value astronomers had been using for over a century, a difference roughly equivalent to the mass of Mars, missing from a planet the size of Neptune. It doesn't sound like much. It was more than enough. In 1992, astronomer Miles Standish plugged the corrected mass into the old orbital calculations, and the irregularities in Uranus's orbit that had launched Lowell's entire quest simply vanished. There had never been a hidden planet pulling on Uranus. There had only ever been a slightly wrong number for how heavy Neptune was, entered into equations decades before anyone had the means to check it. Pluto's discovery was real. It was also, by Lowell's own logic, a coincidence, a genuine world found by a genuinely flawed method, sitting almost accidentally in the neighborhood the bad math had pointed toward. Some researchers who have revisited the numbers since have called it exactly that, a lucky find in the right general area for the wrong specific reason. So now there were two templates for what the math points to an unseen planet can mean. Sometimes it means Neptune, a real discovery, precise to within 1 degree, and sometimes it means Pluto and Planet X, a real object, wrong conclusion, and 70 more years of searching for a phantom that was never there to begin with. Keep both of those stories in your head, because the next one, the one that's actually still unfolding, is going to ask you to decide, in real time, which pattern it's following. For most of the 20th century, the edge of the solar system meant Pluto and not much else. It stayed that way for 62 years, an entire generation of astronomers who grew up with a 9-planet solar system and no reason to think there was anything else worth looking for out there. What finally broke that silence wasn't a new mathematical prediction. It was better equipment. Tombaugh had spent the better part of a year manually flickering between photographic plates, and each pair of plates alone took hours to compare by eye. By the early 1990s, astronomers had traded photographic film for electronic light detectors, CCDs, the same basic technology now sitting inside every digital camera and phone, which captured roughly 9 times more of the available light and could be compared virtually, on a screen instead of by hand. In August of 1992, using exactly this kind of setup on a telescope in Hawaii, astronomers David Jewett and Jane Liu found a faint, slow-moving object well beyond Neptune's orbit. They called it 1992 QB1. It was the first confirmed member of the Kuiper belt found since Pluto itself, proof that Pluto hadn't been a lonely oddball, but the brightest member of an entire, previously invisible population. Within a few years, dozens more turned up. Within a couple of decades, thousands. That changed in 2004, when astronomers Michael Brown, Chad Trujillo, and David Rabinowitz announced the discovery of Sedna. At the time, the most distant object ever observed in the solar system, named after an Inuit goddess said to live at the bottom of the ocean. Sedna belongs to a category astronomers call extreme trans-Neptunian objects, or ETNOs, a label reserved for a small handful of bodies whose orbits carry them so far from the Sun, at their closest approach, that Neptune's gravity essentially can't touch them. That distinction matters. Most objects drifting around out past Neptune have their orbits shaped, nudged, or eventually flung outward by repeated close passes near Neptune's gravity over millions of years. It's the dominant sculptor of that entire region. Sedna's orbit never brings it close enough for Neptune to have any say in the matter. Something else had to explain why it was shaped the way it was. For a decade, Sedna sat alone, a curiosity without a clear explanation. Then in 2014, Trujillo and a colleague, Scott Shepard, found a second object like it, 2012 VP113, and when they compared its orbit to Sedna's, something clicked. Here's the mechanism in plain terms. Every orbit has a point where it swings closest to the Sun. Picture that point as an arrow, pointing outward from the Sun toward wherever in space that closest approach happens to fall. For most objects out past Neptune, those arrows point in essentially random directions, scattered across the sky the way you'd expect if nothing in particular were organizing them. Sedna and 2012 VP113 broke that pattern. Their arrows pointed in almost exactly the same direction, an angle astronomers call the argument of perihelion, clustered suspiciously close to 0 degrees. Two objects both independently discovered, both aiming their closest approach at nearly the same patch of sky, for no reason anyone could immediately explain. Two data points sharing an alignment wasn't proof of anything on its own. It could still be coincidence. But it was enough to make Trujillo and Shepard propose cautiously that something shepherding these orbits might be out there. A planet perhaps 5 times the mass of Earth, sitting on a roughly circular path, around 250 astronomical units from the Sun. Quietly organizing the neighborhood from a distance without ever being seen directly. That idea might have stayed a footnote. Instead, in 2016, 2 Caltech researchers, Konstantin Batygin and Michael Brown, the same Brown who'd found Sedna 12 years earlier, went back through the data with a wider net. They weren't just looking at Sedna and 2012 VP113 anymore. They pulled in 4 more extreme distant objects with similarly odd orbits for 6 in total and asked a sharper question. Do these 6 objects merely share a perihelion angle? Or does their entire orbital orientation, the physical direction their orbits point in 3-dimensional space, line up as well? It did, tightly. Batygin and Brown calculated that the odds of 6 independent objects randomly aligning this precisely, by chance, was about 0. Percent somewhere in the neighborhood of 1 chance in 14,000. That's not a hint. That's the kind of number that makes a reviewer sit up. Something, they argued, had to be actively holding these 6 orbits in formation, the way a shepherd dog holds a flock together, not by being seen, but by being felt over and over across millions of years. Their proposed explanation was a planet with at least 10 times the mass of Earth on a wide, elongated orbit, tilted relative to the plane the rest of the solar system moves in, and crucially, positioned so that its own closest approach to the Sun sits roughly on the opposite side of its orbit from where the 6 smaller objects make theirs. Not a planet sitting among them, a planet standing guard from across the system, gently sculpting their paths for eons through a slow gravitational tug known as apsidal alignment, the same broad family of effect related to something called the quasi-mechanism that lets a distant massive body herd smaller ones into matching orientations over long stretches of time. The way a slow current can eventually line up every leaf floating on a pond without ever touching a single one of them directly, they gave the hypothetical planet a provisional name that stuck immediately in headlines around the world: Planet 9. The ETNO clustering wasn't the only place people went looking for a signature. Some researchers even combed through decades of tracking data from the Cassini spacecraft, which orbited Saturn for 13 years, checking whether a distant, unseen planet's gravity might have left a faint, measurable fingerprint on Cassini's own trajectory. The results were suggestive, not conclusive, a small, unexplained residual in the spacecraft's orbit that could theoretically fit with a planet in roughly the right region, but nowhere near precise enough to count as confirmation on its own. It became one more data point in a growing pile of maybe, never quite a yes, never quite a clean no either. It was, in structure, almost a perfect echo of 1846, an unexplained pattern in the orbits of known objects, worked backward into a prediction about something nobody had ever seen. Badigeon and Brown even said as much themselves, drawing the Neptune comparison explicitly in their own paper. But echoes aren't proof, and this is where the story splits into the tension that's still, right now, unresolved. Not everyone was convinced the 6-object alignment was really evidence of a planet at all. A team led by Corey Schenkman published a rebuttal arguing that the clustering could be an illusion created by where astronomers had actually pointed their telescopes, survey bias, not gravity. If you only look for these objects in certain patches of sky, Schenkman's team pointed out, you'll naturally find the ones that happen to be there, and they'll naturally look clustered, whether or not anything is shepherding them. They calculated that for the clustering to be real rather than an artifact of where surveys had searched the outer solar system, would need to be hiding a much larger population of similar objects than most models predict, enough raw material in fact, to make the whole picture considerably messier than Badigeon and Brown's clean 6-object story suggested. So, is Planet 9 the next Neptune, real, and simply waiting for the right telescope to be pointed at the right patch of sky? Or is it the next Planet X, a compelling piece of math, chasing a pattern that a bigger dataset will eventually explain away, the way Uranus's irregularities turned out to be nothing more than an outdated number for Neptune's weight? For most of the past decade, that question sat mostly still, argued over in journals, while the observations needed to settle it stayed just out of reach. Proposed search after proposed search came up empty, not because the hypothesis had been ruled out, but because no instrument existed that could scan enough sky, deeply enough, quickly enough, to actually test it properly. A hypothesis that can't be tested isn't wrong. It's just stuck exactly where Planet X sat for most of the 20th century, and exactly where Neptune sat for the few months between Leverrier's calculation and Gala's telescope. That changed recently, and not quietly. A newly identified object, announced only this year, found by searching back through old telescope data rather than through new dedicated observations, turned out to share Sedna's basic type of orbit, the same extreme distance, the same detachment from Neptune's influence, but not its alignment. It sits in roughly the right general region of the outer solar system. It does not line up with the other 6 objects that built the entire case for Planet 9 in the first place. That single object doesn't answer the question. If anything, it complicates it further, and we'll come back to exactly why once we've walked through what it means for the shape, size, and location the hypothetical planet would need to have. For now, what matters is this: the clustering that started this whole hypothesis was clean. It isn't perfectly clean anymore, and for the first time since Batajan and Brown published their paper, an instrument exists that was built specifically to settle this question one way or the other, and it has just started watching the sky in earnest. Every previous chapter in this story ended the same way: decades of waiting for the right tool. Leverrier had his telescope within weeks. Lowell never lived to see his. Harrington died still searching. This time, the wait might finally be over, and what that instrument is built to do what it's already found in its first months of operation, and why one particular piece of new evidence has some astronomers rethinking the entire shape of the hypothesis, is where we pick up next. Every previous chapter in this story ended the same way: decades of waiting for the right tool. Leverrier had his telescope within weeks of finishing his math. Lowell never lived to see his. Harrington died still searching. For most of the time Planet 9 has existed as a hypothesis, the same problem applied. The object being searched for was simply too faint, too slow, and too far away for any existing survey to rule it in or out with any confidence. That changed in a very literal sense this year. High in Chile's Atacama Desert, on a mountain called Cerro Pachon, sits the Vera Rubin Observatory, a joint project of the U.S. National Science Foundation and Department of Energy, decades in the planning and construction, named for the astronomer whose careful measurements of galaxy rotation first revealed the gravitational fingerprint of dark matter. At its heart is the Simony Survey Telescope, an unusual 3-mirror design, an 8-meter primary working alongside a 5-meter and a 3-meter mirror, paired with a camera about the size of a small car, a 3-gigapixel imaging system, the largest digital camera ever built for astronomy. A single exposure from that camera captures enough detail that projecting one image at full resolution would require hundreds of ultra-high-definition television screens side by side. The whole assembly can swing to an entirely new patch of sky and steady itself again in about 5 seconds, which is part of what lets it cover so much ground so quickly. The telescope's entire mission, called the Legacy Survey of Space and Time, is built around a deceptively simple idea: photograph the same patch of sky over and over every few nights through 6 different color filters for 10 straight years, and compare each new image to everything that came before. Software does the comparing automatically, a technique called difference imaging. Subtract yesterday's picture of a given patch of sky from tonight's, and anything that hasn't moved cancels out: stars, distant galaxies, all the fixed wallpaper of the universe disappears from the comparison. What's left is only what changed: a supernova flaring to life, an asteroid drifting past, or, hypothetically, a very slow, very faint point of light nobody has ever tracked before. Inching across the frame at a pace consistent with an object hundreds of times farther from the sun than Earth is. This is Tombaw's blink comparator, scaled up by a factor that's difficult to put into perspective. Where Tombaugh examined a bit over 1 million points of light by eye across the better part of a year, Rubin's system is designed to process up to 10 million individual alerts of something changed here in a single night. Sorted automatically by machine learning software trained to separate the interesting handful from everything else. It will map almost the entire visible southern sky roughly every 3 to 4 nights, logging somewhere between 10 and 20 terabytes of new data on a typical night, the rough equivalent of hundreds of feature-length films, recorded as sky instead of story, night after night for a decade. That scale of ambition comes with a very down-to-earth complication. Low Earth orbit satellite constellations, SpaceX's Starlink network chief among them, with several thousand satellites already in orbit and many more planned, leave bright, reflective streaks across long-exposure images. Some estimates suggest as many as 3 in 10 of Rubin's images could eventually show at least one such streak. Engineers at the observatory have been building software specifically to identify and mask these artifacts without discarding the faint, genuine signal sitting underneath them, an entirely modern problem that Leverrier, Tombaugh, and even Batygin and Brown never had to contend with. Getting to this point took time. The observatory released its first test images in 2025, then spent much of that year and into 2026 in a commissioning phase, fine-tuning the camera, the software, and the telescope's mechanics, while already recording early scientific results almost as a side effect. Engineers began issuing automated alerts from the system in February of 2026, and by early spring, teams analyzing the observatory's preliminary data had already logged more than 11,000 new asteroids, including roughly 380 previously unknown trans-Neptunian objects, a haul that in earlier decades might have taken a generation of astronomers to compile by hand. This year, the observatory formally began its 10-year survey in earnest, moving from testing into the actual, dedicated hunt. Planet 9 is far from the only reason Rubin exists. Its primary mission is mapping billions of galaxies to probe the nature of dark matter and dark energy, cataloging the Milky Way, and watching for far more common transient events like supernovae. But among planetary scientists specifically, few open questions carry the same weight. And one advantage has quietly stacked in the hunt's favor over the past decade. Repeated analysis of the known ETNO's orbits has narrowed the plausible search region down to a small fraction of the sky Batygin and Brown were originally working with in 2016, well under a tenth of the original area, meaning Rubin's methodical patch-by-patch coverage doesn't have to search everywhere equally. It can spend disproportionate time on the region most likely to matter. Rubin's reach isn't limited to nearby debris either. During its commissioning period in the second half of 2025, the telescope unknowingly photographed 3I Atlas, only the third interstellar object ever confirmed passing through the solar system, and first spotted by a separate survey, the Asteroid Terrestrial Impact Last Alert System, on the 1st of July 2025. Once astronomers went back through Rubin's own commissioning images, they found the object sitting there already, captured multiple times between late June and early July, days before anyone official had noticed it at all, along with several more incidental sightings over the following weeks. A team led by astronomer Colin Orion Chandler later published the full analysis of those serendipitous observations, describing how they'd used Rubin's early data to help pin down the interstellar visitor's orbit and structure, even though the observatory's own pipeline for tracking fast-moving solar system objects wasn't fully up and running yet. Nobody was looking for 3I Atlas when Rubin recorded it. The telescope caught it anyway, simply because it happened to be scanning that patch of sky at the time. That's the kind of net this instrument casts, wide enough to snag things nobody was specifically hunting for, months before its dedicated 10-year survey had even formally begun. Which raises the obvious question: if a hidden ninth planet really exists, within the range of mass and distance the clustering evidence points to, can this telescope actually find it? Researchers who have spent their careers on this hunt are cautiously, specifically optimistic. Scott Shepard, one of the astronomers who helped uncover the original clustering pattern, has estimated the odds at somewhere around 70 to 80%. Assuming the planet exists within the region the data currently points to, and assuming it behaves the way an ordinary planet should. He's also been careful to flag the uncertainty underneath that number. Nobody knows the planet's exact size or how much light its surface would actually reflect, and if it turns out to be smaller, darker, and farther away than the current best guess. It could sit right at the edge of what even Rubin can detect. Other researchers working directly with the observatory's early data have offered similarly bounded optimism. Astronomer Megan Schwamm and planetary scientist Pedro Bernardinelli have both suggested that if Planet 9 sits within the currently predicted search region, Rubin should turn up a candidate within its first year or two of full operation. If it's really there, Schwamm has said, it should look the way Pluto does in Rubin's images, a modest, steady pinprick of reflected light, sitting exactly where the orbital mechanics say it should. There's a rough number attached to that pinprick, too. Based on current estimates of its size and distance, Planet 9 is expected to have an apparent brightness fainter than magnitude 22, roughly 600 times dimmer than Pluto appears from Earth, and thanks to Kepler's second law, statistically more likely to be found somewhere near the farthest point in its elongated orbit, where an object spends most of its time moving slowly rather than near the point where it swings in closer to the Sun. It's also worth being honest about what's already been tried and come up empty. Dedicated optical searches, including a multi-year survey using the Astrophysical Observatory of Javalamber in Spain, scanned large sections of the predicted search area in 2022 and 2023 without turning up a candidate. Searches through archived data from instruments built for entirely different purposes, including the Atacama Cosmology Telescope, have come back empty as well. None of that rules Planet 9 out. It simply means the search so far has been narrowing down where it isn't, patch by patch, the same slow process every planet hunt in this story has required. Michael Brown, one half of the team that formally proposed the hypothesis, has said he's about as confident as a scientist, allows himself to sound that Rubin represents the best tool anyone could design specifically for this search. If you handed him unlimited funding and told him to build one telescope for exactly this purpose, he said he'd build something very close to what's now sitting on that mountain in Chile. But notice the conditions buried in that optimism: if it exists within the expected region, and if it behaves the way an ordinary planet should. Rubin finds things by watching for reflected sunlight, the same basic principle every optical telescope has used since Galileo. A planet, no matter how faint or how far, reflects at least some sunlight back toward Earth, and given enough exposure time and a sharp enough eye, that faint reflection becomes detectable. That single assumption, that whatever's out there reflects light the way a planet should, is doing a tremendous amount of quiet work in the case for Rubin's success. And it's exactly the assumption one very different hypothesis calls into question entirely. Here's a detail about the Planet 9 hypothesis that rarely makes it past the headline. In the decade since Badajian and Brown first proposed it, dedicated searches using some of the most sensitive telescopes on Earth and in space have found precisely nothing. not a faint smudge. Not a promising candidate that fizzled on follow-up. Nothing. For a world supposedly several times the mass of Earth, that's a strange kind of silence. Strange enough that in 2019, two theoretical physicists, Jacob Scholz at Durham University and James Unwin at the University of Illinois at Chicago, asked a question that sounds almost like a trick. What if the search keeps failing because we're looking for the wrong kind of object entirely? Their starting point wasn't the outer solar system at all. It was a completely unrelated data set, a gravitational microlensing survey called OGLE, the Optical Gravitational Lensing Experiment, a Polish-led program that has spent decades watching dense fields of background stars, mainly toward the center of the galaxy, for the brief telltale flicker caused by something massive drifting in front of them, bending their light just enough to register as a momentary brightening. OGLE wasn't built with Planet 9 in mind at all. Its original purpose was hunting for dark matter candidates and exoplanets using exactly this lensing technique. Over 5 years of that unrelated data, the survey had turned up more of these brief flickers than astronomers expected, evidence it seemed for a population of free-floating objects out in the galaxy with no host star, each with a mass somewhere between roughly half and 20 times that of Earth. Nobody could say for certain what these objects actually were. They don't emit their own light. They don't reflect enough of anything to be seen directly. The only reason anyone knows they exist at all is the way their gravity occasionally, briefly, distorts the light of something behind them. Scholz and Unwin noticed something. That mass range, roughly Earth to 20 Earth masses, sits almost exactly on top of the mass range Batygin and Brown had calculated for Planet 9, calling that a coincidence started to feel like a stretch. So they proposed something stranger than a stretch. What if Planet 9 isn't a planet at all, but a primordial black hole, a relic left over from the earliest moments after the Big Bang when tiny, extraordinarily dense pockets of the early universe are theorized to have collapsed directly into black holes long before any star had formed, lived, or died to produce one the ordinary way. This isn't a fringe idea invented purely to rescue a stalled planet hunt. Primordial black holes have been a serious candidate for a much bigger open question in physics for decades: what dark matter actually is. Nobody has ever directly detected a single particle of dark matter, despite an enormous, well-funded, decades-long search. A population of ancient, planet-mass black holes drifting quietly through every galaxy, including our own, remains one of the few explanations that doesn't require inventing an entirely new particle nobody has ever seen. If the sun happened to capture one of these relics into a long, eccentric orbit sometime in the solar system's early chaotic youth, a period when close stellar encounters were far more common than they are now, the result would look gravitationally exactly like Batygin and Brown's hypothetical planet. A black hole with 5 to 10 times Earth's mass sounds enormous. Physically, it would be almost comically small, an object with roughly the diameter of a bowling ball. All of that mass compressed into a sphere you could, in principle, hold in 2 hands, assuming you found a way to survive the experience. Captured by the sun's gravity billions of years ago, drifting on the same kind of wide, eccentric orbit the clustering evidence already points to, an object like that would tug on the 6 far-flung ETNOs exactly the way a planet would. Gravity doesn't care what's producing it. A black hole of the right mass at the right distance pulls just as hard as a planet of the same mass would, and crucially, it would explain the silence. A planet reflects sunlight. A black hole, by definition, doesn't emit or reflect anything in visible light at all. Every optical survey ever pointed at the region where Planet 9 should be, and there have been several, including painstaking searches through infrared sky surveys, has been looking for a reflection that, under this hypothesis, was never going to be there to find. It wouldn't be a failure of the search. It would be a search built on the wrong assumption from the very beginning. Konstantin Batygin himself, one of the two researchers who put Planet 9 on the map in the first place, has weighed in on his own hypothesis's stranger rival. It's possible he's acknowledged, but there currently isn't any more evidence favoring a black hole than favoring any of the other proposed explanations. That's a fair and fairly rare kind of scientific honesty, the person with the most reason to defend the real planet version of the story declining to dismiss the alternative outright. Scholz and Unwin didn't claim certainty, quite the opposite. Scholz has been candid that, at this stage, there's no strong reason to favor the black hole explanation over the planet explanation, or vice versa. Both remain live possibilities resting on indirect evidence. But the hypothesis does something valuable. It offers several independent ways to actually go looking, using instruments built for entirely different purposes. If a primordial black hole, several Earth masses heavy, is sitting out past Neptune, it should be dragging along its own halo of dark matter. And particle collisions within that halo could in theory produce a faint but detectable trickle of gamma rays, precisely the kind of signal the Fermi Gamma Ray Space Telescope was built to catch, even though nobody designed it with this search in mind. Physicist Edward Witten went further still, proposing a fleet of small probes pushed outward by nothing but the gentle pressure of sunlight that could in theory be steered close enough to a candidate black hole to detect it directly, though other researchers examining the idea more closely concluded that any real signal would likely be drowned out by ordinary interstellar noise long before it reached a detector that far from home. There's a more immediate test, though, and it belongs to Rubin specifically. Astrophysicists Amir Suraj and Avi Loeb proposed that if a small black hole is orbiting out there, it should occasionally have a close encounter with a comet or another small icy body drifting through the same region, and when that happens, the object would be torn apart and briefly heated, producing a short bright flare of light. That's precisely the kind of transient event Rubin's alert system is already built to catch, night after night, as a matter of routine, according to their analysis published in the astrophysical journal Letters. Rubin's survey data should be capable of confirming or ruling out the black hole version of Planet 9 within roughly the first year of full operation, a timeline that notably is faster than the 1 to 2 years researchers have suggested it might take to spot an ordinary reflective planet doing nothing more dramatic than sitting still and shining faintly, which leaves the hunt at an unusually honest kind of crossroads. If Rubin's optical survey eventually finds a faint, slow-moving point of light exactly where the clustering evidence predicts, that resolves things cleanly in the planet's favor, case closed, in the tradition of Leverrier and Gala. But if a decade of the most thorough optical survey ever built comes up empty in that same region, it won't necessarily mean Planet 9 doesn't exist. It might just mean the entire search has been looking for the wrong kind of shadow. Either answer, astrophysicist Avi Loeb has pointed out, would matter far beyond settling an argument. The outer edge of the solar system is, relatively speaking, our own backyard, and finding something massive quietly orbiting out there, whether it turns out to be a planet or a black hole, would be a little like discovering a relative living, unnoticed, in a shed behind a house someone has lived in their entire life. It would immediately raise a longer list of questions than it answers: how it got there, what it's made of, whether it shaped the solar system's history in ways nobody has yet considered, and whether there might be more than one. While Rubin was still in its early commissioning phase, another discovery arrived from a completely different direction, not from a telescope hunting for planets, but from a survey hunting for fossils. A Japanese-led project called FOSSIL, short for Formation of the Outer Solar System, an icy legacy, has spent years using the Subaru telescope in Hawaii to search for exactly the kind of distant ancient, undisturbed objects that Sedna represents, relics that have barely changed since the solar system's earliest days precisely because they orbit so far out that almost nothing has ever perturbed them. In the spring and summer of 2023, the fossil team, led by astronomer Fumi Yoshida, spotted one of these relics in 3 separate sets of observations. On its own, 3 sightings weren't enough to pin down a reliable orbit for something moving this slowly. Determining whether a body actually belongs to the sednoid family, rather than some more ordinary class of object, typically takes about a year of careful, repeated tracking. So the team kept looking, both forward and backward. Additional tracking with the Canada, France, Hawaii telescope in mid-2024 nailed down the orbit with enough precision to search old archives for earlier, unrecognized sightings of the same object. They found it sitting unnoticed in images going back to 2021 to 2014, and further still, all the way back to a set of Kitt Peak National Observatory exposures from 2005, taken nearly 2 decades before anyone realized what they'd captured. They designated it 2023 KQ-14 and nicknamed it Ammonite, after the fossilized sea creature, in keeping with the survey's theme. The discovery was formally shared with the Minor Planets Center in the spring of 2025, and a full paper describing it appeared in the journal Nature Astronomy in July of that year. Ammonite turned out to be only the 4th sednoid ever confirmed, joining Sedna, 2012 VP-113, and one other extreme, detached object in an extremely exclusive club of bodies, whose orbits carry them so far from the Sun that Neptune's gravity simply can't reach them. Ammonite's own orbit swings as close as 66 astronomical units from the Sun at its nearest, and stretches out to a semi-major axis of roughly 252 astronomical units. Tilted about 11 degrees from the plane, the rest of the solar system orbits in a body somewhere between 220 and 380 kilometers across by the team's best estimate. On its own, a 4th sednoid would have been a quiet, welcome addition to the catalog, more data, more confirmation that Sedna wasn't a fluke. What made Ammonite worth an entire chapter of this video is where its orbit points. Remember the mechanism from Part 1. Sedna and 2012 VP-113 lined up so tightly, in the direction their closest approach to the Sun pointed, that the odds of coincidence were calculated at roughly 1 in 14,000. That alignment expanded to include 4 more objects is the entire foundation Batygin and Brown built the Planet 9 hypothesis on. Ammonite's orbit does not line up with that alignment, not approximately, not roughly. It points in a meaningfully different direction than Sedna, 2012 VP-113, and the other clustered objects, a 4th sednoid that, by simple logic, should have reinforced the pattern, instead sitting slightly, stubbornly outside it. Researchers analyzing the discovery have been careful not to oversell what this means. Yukun Huang, an astronomer at the National Astronomical Observatory of Japan, who ran orbital simulations on Ammonite's trajectory, put it plainly in the aftermath of the announcement. An orbit this misaligned with the others lowers the likelihood of the original Planet 9 hypothesis holding up exactly as proposed. That's not the same as ruling it out. Huang and others have floated a handful of ways to reconcile the new data. It's possible a version of Planet 9 still exists, but sits farther out than the original estimates suggested, distant enough that its gravitational grip on Ammonite, specifically, would be too weak to pull its orbit into line with the others, while still shaping the closer six. It's also possible, more provocatively, that a planet-sized object did once occupy that region of the outer solar system and helped sculpt the earlier alignment, only to be gravitationally ejected entirely sometime in the deep past, leaving the pattern behind without leaving the planet behind to explain it. Neither of those explanations is confirmed. Both remain, explicitly, hypotheses being tested against a small and still growing dataset, exactly the kind of open, unresolved tension that separates this story from a settled fact. What Ammonite has done, concretely, is shift where the hunt needs to look, though even that shift isn't unanimous. Simulations run in the wake of Ammonite's discovery, incorporating its misaligned orbit, increasingly favor a planet sitting farther out than the original 2016 estimate. Potentially out toward 500 astronomical units, pushing the likely search radius outward into exactly the kind of extreme faint distances that only an instrument with Rubin's combination of sky coverage and depth stands a real chance of covering thoroughly. Not every research group agrees on that direction, which is precisely what makes this an active scientific debate rather than a settled sequence of updates. A separate 2025 analysis led by astrophysicist Amir Suraj alongside Christopher Chiba and Scott Tremaine ran an expanded set of 51 extreme trans-Neptunian objects through 300 orbital simulations and arrived at a noticeably different answer: a semi-major axis of roughly 290 astronomical units, give or take 30 in eccentricity around zero. And an inclination of only about 6 degrees, a planet sitting considerably closer in than the Ammonite-driven estimates suggest, and crucially, one whose predicted position falls squarely within the patch of sky Rubin's early observations are already covering. Two serious research groups, working from overlapping but not identical data, currently disagree by a factor of nearly 2 on how far out to even look, which leaves 3 open threads heading into the second half of this story. A telescope built specifically for this hunt, now running at full survey speed for the first time, already carrying 2 competing predictions for where to even point its attention. A rival hypothesis suggesting the whole search might be aimed at the wrong kind of object altogether, one that, unlike the planet hypothesis, could be tested and settled within the same 12 months. And a single, stubborn, recently discovered world that doesn't fit the tidy version of the story anyone would prefer to tell, and that has already pushed 2 serious research teams toward 2 different corners of the same dark sky. None of these threads resolve each other. If anything, each one sharpens what the others are actually asking. A confirmed planet would settle Skolt's and Unwin's question immediately, without needing a single gamma-ray detector. A confirmed black hole would explain, instantly and completely, why a decade of optical searching has found nothing at all. And whichever answer turns out to be correct will still have to explain Ammonite, a small, icy fossil from the solar system's infancy that, so far, agrees with absolutely nobody's tidy version of events. All 3 of those threads are still live, still being argued over in current research, in papers published within the last year, and all 3 are about to collide with whatever Rubin's cameras record next. Suppose for a moment that Planet 9 turns out to be exactly what Batygin and Brown proposed, a real, solid 5 to 10 Earth mass world sitting on that wide, tilted orbit hundreds of astronomical units from the Sun. That answer immediately opens a stranger question underneath it. Planets don't form out there. The material needed to build something several times the mass of Earth, gas, ice, rock, all of it was never present in meaningful quantities at 400, 600, 800 times Earth's distance from the Sun. The original disk of gas and dust that built the solar system simply thinned out to almost nothing well before reaching those distances. Whatever Planet 9 is, it almost certainly didn't grow up where it currently lives. Something would have had to move it there, and move it a very long way. One leading idea reaches back into the solar system's own violent adolescence. In 2005, a group of planetary scientists working in Nice, France, Alessandro Morbidelli, Rodney Gomes, Cleomenes Tsiganis, and Harold Levison proposed what's now simply called the Nice model, a reconstruction of the outer solar system's early history in which Jupiter, Saturn, Uranus, and Neptune didn't form in their current orbits at all, but migrated into them from a more tightly packed original configuration. As Jupiter and Saturn's orbits gradually shifted and eventually crossed a specific orbital resonance, the whole outer solar system's gravitational balance tipped into a relatively brief, chaotic phase, the giant planets orbit scattering both each other and an enormous surrounding disk of leftover icy debris left over from the solar system's construction. The model did real explanatory work. It accounted for the so-called late heavy bombardment, the wave of impacts recorded in lunar craters roughly 4 billion years ago, a spike in cratering that puzzled planetary scientists for years, since it didn't match a simple, steady decline in leftover debris from the solar system's formation. A sudden burst of orbital chaos among the giant planets, scattering a reservoir of icy bodies across the entire inner solar system all at once, offered a far cleaner explanation than anything proposed before it. It explained why the Kuiper belt has the particular shape, edge, and population it does today, including its cold classical region of gently orbiting undisturbed objects, a part of the belt that needed to be left almost entirely alone by the chaos happening everywhere around it. Which turns out to be a surprisingly delicate thing for any model to reproduce correctly. It's worth understanding, briefly, what actually triggered that chaos in the first place, because the same forces are doing the throwing in every version of this story. Jupiter and Saturn in this model started out closer together and farther from the Sun than they sit today, gradually drifting apart as they exchanged gravitational energy with the surrounding disk of debris. At a certain point, their orbital periods crossed a specific ratio, Jupiter completing exactly 2 orbits for every one of Saturn's, a configuration called an orbital resonance, where the 2 planets' gravitational tugs on each other stop, averaging out over time, and instead reinforce each other cycle after cycle. Like repeatedly pushing a swing at exactly the right moment to send it higher and higher. That resonance crossing is what tipped the entire outer solar system from a calm, orderly configuration into several million years of genuine chaos, Uranus and Neptune's orbits swinging wildly, the surrounding disk of icy debris scattering in every direction, and in the 5-planet version of events, one entire world getting thrown clear off the gravitational map. A later refinement of that same model adds a wrinkle directly relevant to this story: a 5th giant planet. In this version, the early solar system briefly held 5 outer worlds instead of 4, an extra ice giant, likely 10 to 20 Earth masses, sitting somewhere between Saturn and Neptune's current positions, similar in composition to Uranus and Neptune themselves. As the giant planets migrated and their orbits grew unstable, gravitational encounters between them flung this 5th world outward, hard, on a timescale of roughly 10,000 years, a geological instant, over almost as soon as it began. In most versions of this story, the 5th giant simply leaves the solar system, entirely ejected into interstellar space, gone for good. One of what should be an enormous population of rogue, planets wandering the galaxy with no star of their own, a fate that computer models suggest has probably happened to several other worlds across the solar system's history worlds we'll simply never have any record of. But simply leaving isn't the only possible ending. Michael Brown weighing in publicly on the resemblance between his own hypothesis and this older model has said there's a real chance Planet 9 simply is that fifth giant, not fully ejected, but only partially so. Its orbit stretched out to a wide eccentric ellipse instead of severed from the Sun altogether. Battigan Brown and a colleague Hayden Betts later ran the numbers more formally and found 4-planet and 5-planet versions of the early solar system reproduce the modern outer planets' orbits with roughly similar success, a few percent either way, which is a careful way of saying plausible not proven. Here's the mechanism that would need to happen for a partial ejection to work, and it helps to picture it the way you'd picture a pinball rattling around a table rather than a rocket launch. A planet flung outward by a close pass near Jupiter or Saturn doesn't instantly settle into a nice, stable, wide orbit. Its initial kick typically leaves it on a trajectory that will either escape the solar system entirely or just as often come swinging back through the inner planets on its next pass, like a pinball ricocheting off one bumper straight toward another, which usually ends in a second final ejection rather than a comfortable retirement at the edge of the solar system. For an ejected world to actually survive out, something has to intervene at exactly the right moment on exactly one of those passes, nudging its closest approach to the Sun outward. Just enough that it stops crossing paths with the very planets that flung it out in the first place before it gets a second fatal encounter. Miss that narrow window, and the planet either escapes into interstellar space for good or gets thrown straight back into the gravitational blender. It just barely survived the first time. Two forces can do that particular job, acting slowly, from outside the solar system entirely. One is a passing star. The Sun did not form in isolation. It was born inside a dense cluster containing several thousand sibling stars, packed closely enough that gravitational encounters between neighboring systems happened far more often in the solar system's first tens of millions of years than they do now. In the comparatively quiet galactic neighborhood the Sun currently occupies, a star passing close enough, at just the right angle, could tug a newly ejected world's orbit outward and detach it from future close encounters, essentially rescuing it from its own escape trajectory. The other candidate is the galactic tide, the extremely gentle but relentless gravitational pull of the Milky Way's overall mass, which acts on anything orbiting far enough from the Sun to feel the galaxy more than it feels the planets. Over hundreds of millions of years, that faint tug can also raise a wide, orbit's closest approach just enough to leave it stranded, safely detached, far from the planets that once nearly threw it away completely. Astronomer Gongji Li and her colleague Fred Adams ran millions of simulations specifically testing how often this kind of rescue actually works. Their conclusion was sobering for anyone hoping for a clean origin story. Even in the most favorable version, a passing star tugging a solar system-born planet into an orbit matching Planet 9's proposed parameters succeeds only around 10% of the time, at best. Far more often, the same stellar encounter that could rescue the planet instead finishes the job its first, violent ejection started, throwing it out of the solar system for good. Think of it less like a single lucky escape and more like a coin that has to land on its edge, technically possible, physically consistent, but not the outcome you'd bet on if you ran the whole scenario over from scratch 1,000 times. Lee and Adams also tested two stranger possibilities directly. that Planet 9 wasn't native to the solar system at all, but an exoplanet stolen from a different star system, entirely during one of those early close encounters, or a genuinely free-floating starless planet that happened to be drifting past at the right moment to be captured. The mechanism for either scenario is roughly the same one that could rescue a native planet from ejection, just run in reverse. Two young star systems still surrounded by their own planets drift close enough to briefly share a gravitational neighborhood, and in the resulting chaos, a planet that belonged to one star ends up gravitationally bound to the other instead. Effectively, a very slow-motion cosmic-scale trade with no one at either star system ever aware an exchange had taken place. Both of those scenarios, Lee and Adams' simulations suggested, carry less than a 2% chance of actually happening. None of those numbers rule anything out. They do mean that if Planet 9 exists, its presence there at all would represent something closer to a narrow escape than an inevitability, a planet that, by most versions of the math, should have been lost entirely and somehow wasn't. This isn't purely theoretical. A real, confirmed object gives this exact mechanism a working example. In 2025, a small team led by astronomer Sihao Cheng at the Institute for Advanced Study, working with Princeton researchers Jiaxuan Li and Eritas Yang, announced the discovery of 2017 OF201, an object they found not through new observations, but by combing through archived telescope images from 2011 through 2018, using a computationally efficient search algorithm. Cheng built specifically to catch exactly this kind of extremely slow, extremely faint motion. Hidden across 19 separate exposures spanning 7 years. Cheng has said the project traces back to a lecture he attended in 2005, given by Michael Brown himself, years before Brown and Batygin would go on to formally propose Planet 9 at all. A nice, quiet piece of continuity running underneath this entire search. Based on its current orbit, a perihelion of about 45 astronomical units and aphelion out beyond 1600, and a semi-major axis near 840. The team's working explanation is that 2017 OF201 was first flung outward by a close encounter with a giant planet, then rescued from full ejection, precisely the way Lee and Adams described theoretically. Its orbit gradually detached and stabilized by the combined patient influence of galactic tides and passing stars over billions of years. Whatever pushed Planet 9 outward, if it exists, this newly confirmed neighbor suggests the mechanism itself is real and has happened at least once already, to at least one other world we can actually point a telescope at. Co-discoverer Eritas Yang has estimated that if one object like this survived the process and got lucky enough to be caught during its brief, detectable window near the Sun, there are likely hundreds more just like it, still hidden, simply too far away right now to be seen. If Planet 9 exists, here's the physical portrait current models converge on. A world with somewhere between 5 and 10 times Earth's mass, a radius 2 to 4 times Earth's own, and a surface temperature hovering around -230 degrees Celsius, a body scientists sometimes describe as sitting in the same general size and mass category as the super-Earths and mini-Neptunes that strangely show up constantly around other stars in the galaxy, yet are completely absent from our own solar system's actual planetary lineup. Surveys of exoplanets across the galaxy have found that this exact size range, bigger than Earth, smaller than Neptune, is one of the single most common types of planet known to exist anywhere. Our own solar system appears to be missing one entirely. If Planet 9 is real, it wouldn't just be a new discovery. It would fill a category of world that had, until 2016, gone completely unnoticed in our own backyard, while turning up constantly everywhere else astronomers have looked. There's a piece of irony worth sitting with here, too. Michael Brown, the same researcher pushing hardest for Planet Nine's existence, is the same astronomer whose 2005 discovery of Eris, a Kuiper Belt object briefly thought to be larger than Pluto, directly triggered the International Astronomical Union's 2006 decision to formally define what a planet actually is, a definition that promptly reclassified Pluto out of the category entirely. That definition requires a planet to have gravitationally cleared its own orbital neighborhood of other debris. It's a genuinely open question whether a world sitting alone at 3, 5, or 800 astronomical units, with only a small, thinly scattered population of ETNOs anywhere near it, would even qualify under the same rule that cost Pluto its title. The person who built the case for demoting 1/9 planet is now building the case for finding an entirely different one, and if he succeeds, the new candidate may have to clear the exact same bar that the old one failed. Its orbit is where the real scale of this becomes difficult to hold in your head all at once. Current estimates place its semi-major axis somewhere between roughly 300 and 800 astronomical units, with different research teams currently favoring different ends of that range. As the last two chapters covered, and an orbital eccentricity stretched out enough that its distance from the Sun varies dramatically over the course of a single lap. Do the math on an orbit that size using nothing more exotic than the same equations that predicted Neptune in 1846. And the number that comes out the other end is almost hard to process emotionally, somewhere between 10,000 and 20,000 years to complete one single orbit around the Sun. Sit with that for a second. 10,000 years ago, the last ice age was only just loosening its grip on the northern hemisphere. Agriculture had not yet been invented anywhere on Earth. 20,000 years ago, most of what's now Canada, Scandinavia, and northern Europe sat under kilometers of ice. Sea levels sat roughly 120 meters lower than they do today, and no human being anywhere had yet developed writing, pottery, or permanent settlements of any kind. If Planet 9 exists and is anywhere near its farthest point from the Sun right now, the last time it swung through that same point in its orbit, nothing recognizable as civilization existed anywhere on the planet watching it. Every empire, every language currently spoken, every city on Earth has been built, in its entirety, within a single slice of this one hypothetical planet's year. That number isn't a stretch of the imagination built for a hypothetical world. There's already a confirmed example of exactly this kind of timescale sitting in the sky right now. That same 2017 OF201 discussed a moment ago has a measured orbital period of roughly 24 to 25,000 years, a number derived from an actual tracked orbit, not a model. Its closest approach to the Sun, the one point in its enormous loop, where it's actually bright enough to be seen at all, last happened in November of 1930, the same year coincidentally. That Clyde Tombaugh discovered Pluto using a blink comparator a few hundred kilometers from where this video already spent an entire chapter. Before that, the last time 2017 of 201 swung this close to the Sun was roughly 24,250 years earlier, right around the time the first humans are thought to have been making their way into North America across the land bridge from Siberia. This object has completed exactly 2 close approaches to the Sun in the entire span of time since people first walked onto this continent. It spends barely 1% of each orbit close enough to Earth to be detected at all, which is precisely why nobody noticed it in real time and had to find it, after the fact, buried in 7-year-old archived photographs instead. If a world on that kind of timescale can be real, confirmed, and sitting quietly in old data for years before anyone thought to look for it, then a genuine ninth planet, on a broadly similar kind of orbit, stops sounding like a stretch. It starts sounding like exactly the kind of object this particular, mostly empty region of space is evidently capable of hiding. It would be tidy to end this chapter there, on that scale of awe. It wouldn't be honest. Not every group studying this question agrees the clustering evidence holds up at all. In 2022, major independent surveys, the Outer Solar System Origins Survey, a Canadian-led project that had spent years systematically cataloging the outer solar system with exactly this kind of bias correction built into its design from the start, and the Dark Energy Survey, an American collaboration originally built to study the accelerating expansion of the universe that happened to sweep up a large number of trans-Neptunian objects as a side benefit, published results built on a vastly larger sample than the original 6 objects Batygin and Brown worked from. Between them, these two projects had catalogued more than 1,100 trans-Neptunian objects, well over 1,000 data points instead of a handful. After carefully correcting for the same kind of observational bias Shankman's team had raised years earlier, the simple fact that surveys don't look at every part of the sky equally often, and so naturally find more objects in the regions they happen to search most, both teams concluded they found no statistically significant clustering at all among the objects in their much larger samples. Samantha Lawler, an astronomer involved in that analysis, put the disagreement plainly. Working from just 14 objects, as the original hypothesis effectively did, and drawing firm conclusions from that small a sample, was premature, especially once a dataset nearly 60 times larger failed to reproduce the same pattern. That's not a small disagreement, tucked quietly into a footnote. It's two well-resourced, peer-reviewed survey teams looking at more comprehensive data than the original discovery paper had access to, and coming away unconvinced that there's anything here to explain in the first place. Against that stands researchers like Brown, who has said publicly that he finds it increasingly unlikely Planet 9 doesn't exist given that no competing explanation accounts for the full range of effects he and his colleagues believe they've now identified across the outer solar system, not just the original 6-object clustering, but a broader set of orbital patterns collected in the years since. Both of these positions are held, right now, by working scientists with access to the same broad category of evidence, reading it in two genuinely different directions. So the honest state of this hunt, heading into the story's final stretch, looks like this. A telescope built specifically to settle the question, already running, already carrying two competing predictions for where to even point. A confirmed, real-world object proving the underlying timescales and survival mechanisms aren't just theoretical. A rival hypothesis suggesting the whole search might be aimed at the wrong kind of object entirely, testable within the observatory's first year of full operation. And a larger, more skeptical body of survey data suggesting that the pattern which started this entire chase 11 years ago might not have been a pattern at all. None of these threads have resolved. All of them are converging, right now, on the same handful of years, the first years this generation's most capable telescope has actually been switched on and pointed at the sky. Every scenario this video has walked through so far assumes the hunt is still open. It's worth pausing briefly to ask what actually changes the moment it isn't, the moment a faint, slow-moving point of light shows up in Rubin's data exactly where the models said it should. The first thing that happens is almost administrative. Planet 9 doesn't have an official name yet, and by International Astronomical Union convention, it won't get one until it's actually confirmed through direct imaging rather than inferred from its gravitational fingerprint. Naming rights would most likely fall to whoever's data produces the confirmed detection, following a long tradition that stretches back to Le Verrier and Gala arguing over credit in 1846. Every full-sized planet named so far has drawn from Roman or Greek mythology: Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, and there's no obvious reason a confirmed ninth planet would break that pattern, whatever the informal nickname that's carried it through a decade of headlines. Then comes the slower, more interesting part, actually going to look at it properly. Michael Brown has floated a specific, almost startling number. Using a close-powered slingshot maneuver around the Sun, a dedicated probe could conceivably reach Planet 9 in as little as 20 years. A fraction of the multi-decade journeys that got the Voyager probes to the outer solar system and New Horizons to Pluto. 20 years sounds fast until you remember the object it's traveling toward takes somewhere between 10 and 20,000 years just to complete a single lap of the orbit that probe would be aiming for, a reminder that even our fastest spacecraft are from the planet's own perspective. Arriving in what would register as an instant, long before any probe could launch, though existing telescopes would go to work characterizing whatever Rubin's cameras first catch. The James Webb Space Telescope, built to see exactly the kind of faint infrared glow a cooling ancient planet would still be radiating from its own formation billions of years ago, is considered one of the strongest candidates for a rapid follow-up campaign, potentially useful for measuring the object's temperature rough size. And even hints of atmospheric composition well before anything resembling a spacecraft could be designed, funded, and launched. Some researchers have gone further, still modeling whether a world this size, this far from the Sun, might retain its own small system of moons, icy bodies up to roughly 100 kilometers across in some published models, the same way every other giant planet in the solar system has accumulated a retinue of satellites over billions of years. That's speculative modeling built entirely on comparison to the planets we already know, not a prediction anyone is confident in, but it's the kind of question that becomes immediately answerable rather than merely interesting the instant confirmation happens, and confirmation would ripple outward past the solar system itself. Astronomers have spent decades cataloging thousands of planets orbiting other stars, and one of the strangest, most consistent findings from that entire body of work is how common planets in Planet 9's proposed size range, bigger than Earth, smaller than Neptune, turn out to be around other stars. And how conspicuously absent that exact category is from our own solar system's current lineup. A confirmed Planet 9 wouldn't just add a ninth entry to a list. It would mean the solar system had been quietly hiding the one type of planet that shows up almost everywhere else in the galaxy, tucked into the one region of sky too faint and too slow for anyone to have properly searched until now. None of that requires Planet 9 to actually exist. It's simply what's waiting on the other side of a single, faint, correctly identified point of light, assuming Rubin's cameras, or whatever comes after them, ever actually find it. The other branch of this story would look almost nothing like that. If Suraj and Loeb's proposed test succeeds instead, if Rubin catches a short, unexplained flare consistent with a small object being torn apart near a compact, invisible mass rather than a steady, reflective point of light drifting across the frame, the celebration wouldn't be about a ninth planet at all. It would be the first direct evidence anywhere of a primordial black hole, a relic of the Big Bang itself, sitting quietly in our own solar system the entire time modern astronomy has existed, mistaken for a missing planet because gravity alone can't tell the difference between the two. That result wouldn't just rewrite the outer solar system's story. It would hand physicists their first real physical specimen of an object type that, until that moment, had existed only in equations, with direct consequences for the decades-long, entirely separate hunt for what dark matter actually is. Two very different discoveries, both hiding behind the exact same gravitational signal, both currently indistinguishable from each other by anything except the specific kind of light or its complete absence that shows up in the data. Whichever one it turns out to be, the search ends the same way every version of this story has ended since 1846, not with more speculation, but with a telescope pointed at the right patch of sky at exactly the right time. Every hunt described so far in this video has, eventually, ended. Neptune was found, Pluto was found, and then quietly disqualified from the role it was found for. The fifth giant, if it ever existed, either left the solar system for good or is still out there somewhere, waiting. Planet Nine's hunt hasn't ended yet, and unlike every story that came before it, this one is still actively developing while this script is being written. That's worth pausing on for a moment. Everything covered in the first 3 parts of this video is settled history, however recent. Everything in this final part is still moving. A team led by Terry Long Fan, a graduate student at National Tsinghua University in Taiwan, working with his advisor Tomitsugu Godu, took an approach nobody else in this video has tried. Instead of hunting for reflected sunlight, they went looking for Planet Nine's own leftover heat. Any planet that size retains warmth from its own formation for billions of years, radiating faintly in far-infrared wavelengths regardless of how much sunlight actually reaches it, a signal that travels directly to Earth instead of making the round trip a reflection requires. Fan and Godu compared 2 all-sky infrared surveys taken 23 years apart, the Infrared Astronomy satellite, launched in 1983, and Japan's AKARI satellite, launched in 2006. A world on Planet Nine's proposed orbit should drift roughly 3 arcminutes across the sky in that gap, slow, but not too slow to catch, if you know exactly what pattern to search for across millions of catalogued points of light. After narrowing an enormous initial dataset down through careful elimination, the team identified one genuinely promising candidate, a source present in the 1983 data, absent from the same coordinates in 2006. And vice versa, consistent with something slow and massive having moved through that patch of sky in the intervening decades. It's the first candidate in this entire hunt that's made it this far through this particular method. And then came the complication, right on schedule for this story. When Michael Brown examined the candidate's implied motion, he found it sitting on a highly inclined, mildly retrograde orbit, tilted sharply away from, and looping in the opposite direction to the plane the rest of the solar system moves in. That's not a minor detail. An object on that kind of orbit couldn't produce the specific gravitational shepherding effect that started this entire investigation in the first place. The clustering of Sedna, 2012 VP-113, and the other extreme trans-Neptunian objects Batagian and Brown built their original case around. Whatever this new candidate turns out to be, Brown has been characteristically direct about it. Even if it's real, it is not the object his own hypothesis predicted. He's floated a lighter name for it, half joking, in case it does hold up under further scrutiny, not Planet 9, but Planet 8. A different resident of the same dark neighborhood, solving a different problem than the one this video has spent 3 parts building toward. Godu himself has been careful not to oversell the finding. 2 detections, 23 years apart, aren't enough on their own to fully pin down an orbit. That requires a third data point, at minimum, and the team has said they're hoping to secure follow-up observations using the dark energy camera to get it. Depending on what that follow-up shows, this candidate could turn out to be exactly what it looks like, a real, previously uncatalogued world, just not the one this entire story has been chasing. Or it could turn out to be noise, or a transient astrophysical event that happened to look, briefly, like exactly the kind of slow-motion astronomers have spent a decade hoping to see. There's something quietly reassuring, even in the uncertainty, about how Brown responded to a result that technically complicates his own life's work. A researcher less secure in his own hypothesis might have been tempted to stretch the data, to find a way to make the new candidate fit the orbit his career depends on. Instead, the response was closer to, interesting, but that's a different question than the one we're asking, and if it holds up, it deserves its own name rather than getting awkwardly folded into ours. That's a small, specific example of exactly the kind of intellectual honesty this whole hunt has required at every stage, the same honesty that let Leverrier's colleagues eventually admit Vulcan wasn't real, and that lets modern researchers hold two live, mutually exclusive explanations for the ET&O clustering in their heads simultaneously without needing to resolve the tension before the data actually arrives. Meanwhile, the search this video has spent the most time on keeps running in the background, in the most literal sense possible. The Vera Rubin Observatory's alert system went live to the public in February of this year, issuing roughly 800,000 alerts on its very first night alone, a number expected to climb towards 7 million a night once the full 10-year survey reaches its stride. And it means something specific. This is not a search locked away in a handful of research institutions, waiting years for a published result. Every alert the observatory generates, every flagged asteroid, every flare, every faint point of light that wasn't there the night before streams out in near real time to a set of publicly accessible software platforms called community brokers, with names like RCE Antares and Lasser, built specifically so that researchers, students, and interested amateurs anywhere on the planet can filter that flood of data for exactly the kind of signal they care about. Through a partnership with the citizen science platform Zooniverse, ordinary members of the public are being invited to help classify some of what the observatory finds. If Rubin's cameras ever do catch a faint, correctly moving point of light in the right patch of sky, there's a real chance the first place it becomes visible won't be a locked research server. It'll be a public data stream anyone with an internet connection could, in principle, be watching. That's a strange note to end a hunt this old on. For 180 years, finding a hidden planet meant one astronomer, one telescope, one letter sent to the right person at the right observatory. This time, whatever the answer turns out to be, thousands of people could plausibly see it arrive at roughly the same moment the scientists do. There's one more chapter to Urbain Le Verrier's story that this video hasn't told yet, and it belongs here, at the end, more than anywhere else. It's the reason no single outcome of the Planet 9 hunt should be treated as the only honest one, and the reason a video built around distinguishing confirmed science from active debate can't responsibly leave this part out, however tidy the story would be without it. Fresh off the triumph of Neptune, Le Verrier turned his attention to a much smaller puzzle, closer to home. Mercury, the solar system's innermost planet, doesn't trace the exact same ellipse around the Sun on every orbit. Its closest approach to the Sun, its perihelion, creeps forward slightly with each pass, a drift astronomers call precession. Some of that drift was expected, accounted for by the gravitational tugging of every other planet in the solar system. But by 1859, Leverrier had calculated the numbers precisely enough to find a stubborn leftover, a small, persistent discrepancy of about 43 arcseconds per century that nothing in Newton's physics could explain. He'd solved exactly this kind of problem before, using exactly this kind of math. So he did it again. Leverrier proposed a small planet, orbiting even closer to the Sun than Mercury, its gravity responsible for the leftover wobble. He named it Vulcan after the Roman god of fire, and the timing could not have looked better, shortly afterward. An amateur astronomer named Edmund Lescarbault reported watching a small dark dot cross the face of the Sun, exactly the kind of transit a planet in Vulcan's proposed orbit should produce. Leverrier was convinced. Vulcan, as far as he and much of the astronomical establishment were concerned, had been found. It hadn't been. Over the following decades, astronomers mounted expedition after expedition, timing their travel around solar eclipses, the only conditions under which a planet that close to the Sun's glare could conceivably be seen at all, to Spain, to the United States, to Africa. Some reported tantalizing glimpses. None held up under scrutiny. By 1908, after a string of careful, dedicated eclipse expeditions turned up nothing conclusive, the director of the Lick Observatory in California stated plainly that the search for an intramercurial planet could be considered closed. Vulcan had never been there at all. That left the original problem completely unsolved, sitting untouched for another 7 years. Something was still bending Mercury's orbit by exactly 43 arcseconds per century, and nothing in the accepted physics of the day could account for it. The eventual answer, when it came, didn't involve a telescope at all. In November of 1915, Albert Einstein finished the equations of his general theory of relativity and used them, almost as a test case, to calculate Mercury's precession from first principles. The number that came out matched the observed discrepancy exactly, not because of an unseen planet's gravity, but because the Sun's own mass gently curves the space around it, and Mercury sitting closer to that curve than any other planet feels the effect more strongly than anything else in the solar system. There was no Vulcan. There had never needed to be one. The missing mass Leverrier spent decades hunting for wasn't missing at all. It was a gap in Newtonian gravity itself, one that needed an entirely new theory of gravity to close, not a new object floating somewhere in the dark. It's worth sitting with the fact that this happened to the same person, using the same method twice, once triumphantly, once not. Leverrier's math found a real, physical, 12,000-mile-wide planet within 1 degree of its predicted position in 1846. 13 years later, working the same kind of problem with the same rigor, the same math pointed confidently at a planet that was never there at all, because the actual answer required throwing out part of the framework the math itself was built on. That's the third possible ending sitting quietly alongside the two this video has already spent hours on. Neptune, the math was right and the object was real. Planet X and Pluto, the math was based on a measurement error, and the object it happened to point toward was real for entirely unrelated reasons. Vulcan, the math was measuring something completely genuine. Mercury really does precess by that exact amount, and the answer was neither a real planet nor a coincidental one. The answer was that the question itself had been posed inside the wrong theory of gravity from the very start. Planet Nine's clustering evidence is real, in the sense that the ETNOs really do share that unlikely alignment, however, that eventually gets explained. Whether the explanation turns out to be a planet, a primordial black hole, an illusion of observational bias, or something closer to Vulcan's fate, a correction to a piece of physics nobody currently suspects needs correcting, depends entirely on what Rubin's cameras and whatever comes after them eventually record. Vulcan's name, at least, didn't vanish entirely. Astronomers still occasionally search that same scorched region between Mercury and the Sun today, not for a planet anymore, but for a hypothetical population of small, stable asteroids nicknamed Vulcanoids, a appropriately modest legacy for a planet that spent 60 years being one of the most confidently reported discoveries in the solar system before turning out to be nothing at all. Step back for a moment from the last 3 parts of this video, and the whole shape of this hunt looks less like a single discovery story and more like the same question, asked over and over by different people with different tools for nearly 2 centuries. It started with a genuinely strange coincidence. A planet, predicted purely through mathematics before anyone had seen it, found within 1 degree of where the math said to look. That success became a template, and the template misfired almost immediately. Percival Lowell's search for Planet X, built on the same kind of orbital reasoning, led to Pluto, a real discovery that solved nothing because the problem it was supposedly solving turned out to be a decades-old rounding error in Neptune's mass. The very same astronomer who triumphed with Neptune tried the identical method a 3rd way on Mercury, and this time the math pointed at a planet that simply wasn't there at all, Vulcan, a phantom, that took nothing less than a wholesale rewrite of gravity itself 60 years later. To finally dissolve, 3 uses of the exact same method, 3 completely different outcomes from evidence that looked, at the time, equally convincing in every case. Then came a genuinely new kind of evidence, not 1 strange orbit, but 6 of them, all pointing in nearly the same direction, at odds too long to explain away as chance. Badigian and Brown's proposal gave that pattern a name and a hypothetical culprit, and immediately inherited the oldest problem in this entire story. A prediction is not a discovery, and the gap between the two, this time, has already outlasted a decade. Into that gap arrived a telescope built specifically to close it, an alternative explanation stranger than the planet. It was meant to replace an ancient icy relic that refused to fit the pattern that predicted it. 10 years of large-scale survey data suggesting the whole pattern might be an illusion of where astronomers happen to look, and as of the writing of this very video, a brand new candidate that might turn out to be real and still somehow answer a completely different question than the one this hunt originally set out to solve. Underneath all of that sits a stranger question this video spent a full part on. Even granting the planet exists, how would it have gotten there at all? The honest answer, gathered from every model currently taken seriously, is that it almost certainly shouldn't have. A world flung outward during the solar system's early chaos should, by the numbers, have either escaped entirely or been thrown straight back into the planets that ejected it in the first place. Survival in a stable wide orbit works out in the most generous simulations available roughly 1 time in 10. And a confirmed neighbor, 2017 OF201, sitting on almost exactly this kind of scarred, rescued orbit, proves that whatever narrow escape this requires has already happened at least once, to at least 1 world we can already see. Every version of this planet's possible existence, in other words, is a story about surviving something that should have erased it. None of that is failure. It's what an honest, unresolved scientific question actually looks like while it's still being worked out in real time, rather than after the fact, once a tidy answer has already smoothed over every false start along the way. Consider, too, everything this hunt has touched without meaning to. It's dragged a decade-old debate about what planet even means back into the open, the same debate that cost Pluto its title. It's forced a genuine, serious hearing for the idea that an object hiding in our own solar system could be a relic left over from the first fraction of a second after the Big Bang. It's turned a Japanese survey looking for icy relics, a Taiwanese graduate student's infrared comparison, and an American graduate student's archival image search into 3 independent, ongoing side investigations, each capable of confirming or complicating the central hypothesis without ever meaning to weigh in on it directly. A question that started as 6 oddly aligned orbits has, by now, pulled in cosmology, general relativity's modern legacy, and the entire architecture of how the outer solar system took its current shape. Very few genuinely open scientific questions manage to touch that much ground at once. It's also worth being honest about how easily a story like this one slides into overconfidence in either direction. It would have been simple to build this entire video around the version where Planet 9 is essentially already found, waiting only on Rubin's confirmation. Plenty of coverage over the past decade has leaned exactly that way. It would have been just as simple to build it around the OSSOS and dark energy survey results and conclude the whole hypothesis was likely dead on arrival. Both of those framings exist right now in published, credentialed, peer-reviewed work. Treating this as settled in either direction would have meant quietly discarding half of what serious researchers currently believe in favor of whichever half made for a cleaner ending. There's a pattern sitting underneath every version of this story, and it has nothing to do with planets specifically. Long before anyone could point a telescope at Neptune, its existence was already there, encoded in the wobble of a planet that could be seen, a signature left behind by something unseen, readable only to whoever thought to go looking for it. That's a strange kind of knowledge to hold, not certainty, not guesswork either, something in between, a conclusion forced into existence by the sheer weight of a pattern that refused to make sense any other way. Every generation since Leverrier has had its own version of that same in-between state. A world learns to read the wobble in a planet's orbit and finds Neptune. It learns to read the flicker of a distant star's light bending around something massive and dark, and starts to wonder whether Planet 9 might be a black hole instead of a planet. It learns to read the faint infrared glow of something that no longer reflects enough sunlight to see directly. Each of those methods is really the same idea, dressed differently. Reality leaves fingerprints on the things we can observe, even when the thing itself stays stubbornly out of view. Learning to read those fingerprints, rather than waiting for something to finally step into the light on its own, might be the single most consistent thread running through the entire history of astronomy. There's a harder lesson sitting right alongside that one, and Leverrier himself is really the only person who ever demonstrated both halves of it personally. The same method, applied with the same rigor, by the same mind, produced Neptune and produced Vulcan, one of the most spectacular confirmations in the history of science, and one of its most instructive false alarms, 13 years apart. Nothing about the second calculation was sloppier than the first. Mercury really was precessing by exactly the amount Leverrier measured. The math wasn't the problem. The assumption sitting underneath the math, that Newton's gravity was the final word on the subject, was. Knowing when a pattern points to a real, findable object, and when it's quietly pointing at a flaw in the theory, doing the pointing is not something the math itself can tell you in advance. It's only visible afterward, once the telescope or the equation finally settles it one way or the other. That's not a flaw in the method. It's the actual shape of doing this kind of work honestly, and it's exactly the position every researcher named in this video is currently standing in. There's something worth sitting with in the fact that this particular fingerprint, 6 objects, quietly pointing in the same direction for millions of years, waiting for anyone curious enough to notice, was sitting in plain sight the entire time telescopes have existed. It didn't require better eyes. It required someone to ask the right question of data that had, in some form, already been collected. The universe isn't hiding Planet 9, if it exists. It's simply indifferent to whether anyone happens to be looking, in exactly the way a system that has always been indifferent to being watched tends to be. Meaning, when it shows up at all in a hunt like this one, doesn't arrive from outside. It gets built, patiently, out of exactly the kind of careful, repeated attention this entire investigation represents. There's also something worth noticing about which part of the universe this particular hunt is actually about. This isn't a search aimed at some distant galaxy, some star system light years away that will never be visited by anything built on Earth. It's a search aimed at the edge of home, the outermost, laced-mapped room of the same house every telescope, every launched probe, every one of these videos ultimately starts from. Neptune, Pluto, Vulcan, and Planet 9 are really the same recurring realization, showing up in 4 different centuries. Even the neighborhood immediately around us is not something anyone has ever finished mapping. There is no point so far at which the outer edge of the solar system has been declared complete, fully inventoried, safe to stop checking. Every time that edge has been examined more carefully, something has been sitting there that the previous generation's instruments simply weren't sensitive enough to catch. It's worth remembering, here at the end, whose name is actually on the Observatory this entire second half of the hunt depends on. Vera Rubin never searched for a hidden planet. She spent her career watching how galaxies rotate. And noticing that they spin in ways their visible matter alone couldn't possibly account for stars at a galaxy's outer edge moving just as fast as stars near its center. A pattern that only makes sense if a vast amount of unseen mass is quietly holding the whole structure together. She never saw dark matter directly. Nobody ever has. Its entire case rests on exactly the same kind of reasoning this whole video has followed from Vera onward. Something invisible, inferred entirely from the way it bends the motion of things that aren't invisible at all. The telescope built to possibly catch Planet 9 in the act carries the name of someone who spent a career finding gravity's fingerprints on things she never got to see with her own eyes either. Maybe that's the more honest way to hold the number from a few minutes ago, 10 to 20,000 years for a single orbit, longer than every written word, every language, every city currently standing, not as a lesson in smallness. As a reminder that the questions worth asking rarely resolve on a schedule convenient to the person asking them, and get answered anyway, eventually, by whoever's still paying attention when the data finally lines up. In 1846, a mathematician calculated exactly where an unseen planet had to be before any telescope confirmed it. He was right. That's where this video began. Whether the story of Planet 9 ends the same way, a real solid world. Waiting patiently in Rubin's data for its own version of that 1-degree confirmation, or ends the way Percival Lowell's search did, folding quietly into a different explanation nobody expected at the outset, or ends the way Vulcan's did, dissolving into a correction of physics itself rather than a discovery of anything at all. The search has already done what every version of this hunt has done since Leverrier first picked up his pen, turned an absence into a question precise enough to actually go looking for an answer. 6 objects, still quietly aligned at the edge of the solar system. A telescope built specifically for this, finally running at full speed. A rival hypothesis testable within its first year. a relic called ammonite that refuses to fit the pattern that predicted it, a dwarf planet candidate whose own 24,000-year orbit proves the timescales here are real. A brand new infrared signal that might be something else entirely. And underneath all of it, the same question Leverrier asked about Uranus in 1846, and asked again, less successfully, about Mercury in 1859. Is something out there bending what we can see, and can the bending itself tell us what it is, before we ever actually see it? The sky hasn't shown it yet. For the first time in this search's history, something is finally watching closely enough that it might not stay that way much longer. If piecing together evidence like this, cosmic mysteries built patiently out of nothing more than orbits, light, and careful arithmetic, is the kind of thing that keeps you coming back, subscribe. It helps this channel reach more people who think the same way. We're genuinely glad you're here. The next video picks up a thread this one has already brushed against more than once. The handful of visitors from other star systems that have already passed straight through our own, and what their brief, uninvited visits have quietly told us about the neighborhood we live in. See you there.